couple of minutes. My name's Jason Vandiver, Energy Code Program Manager for SPEAR. Our speaker today, Gil Rossmiller with Colorado Code Consulting. He, a little bit like me, although it sounds like a much better carpenter than I am, kind of grew up in construction and then has moved on to code enforcement and plan review and consulting. And when it comes to the code, Gil knows about as much as anyone as I've been around. What I really like on his take is he approaches it kind of the way I do, which is I like to live in the real world, and he does too. And you can't build a doghouse to code. You certainly can't build a house to code. And so, you know, blending that fine line of, hey, I've worn the tool belt, and hey, I've written the red tags. And then now, of course, you know, as Energy Code Program Manager for SPEAR, I am a tree-hugging hippie working for an energy efficiency nonprofit. But I like to get speakers such as Gil to we can kind of blend those three worlds together and give some not only what the code says, but hey, if you're not going to do the code, here's some best practices, here's some rules of thumb. And today is going to be all about Manual S. Actually, Gil, I'll go ahead and turn it over to you and let you introduce the session and get started. The floor is yours, good sir.
Sounds good. Sounds like a plan. So yes, Gil Rossmiller here, Colorado Code Consulting. Today it's all about Manual S and a little bit about me, I guess. So as Jason was saying, we were talking before we started here, 40 years. So I started my construction career back in 1975. I was the guy shoveling the sand for the concrete slabs. I kind of worked my way up through the trades, framing and finished carpentry, hanging doors, trim, the whole deal, and had my own company for a decade. A lot of commercial different projects, a lot of residential projects, and now I just got the wood shop at home, spend my time in there. But anyway, been in the code development cycle here for several code cycles, IRC plumbing mechanical for the 9 and the 12, and did commercial energy code development for the 15 and the 18, and most recently the residential for the 21. Code official there in Parker for about 13 years, and 7 years before that I was just their plans examiner and building inspector. So it's been about 20 some years in the field and 20 some years finding code compliance. So that's me. So let's talk about this. Last week we talked about heat gain and heat loss calculations, which is the Manual J piece of it. Okay. This is the next step in our design process, is Manual S. Okay. What we're all going to learn is that none of the current softwares that are out there, so RightSoft and Elite are the two that I'm most familiar with. RightSoft is the software I own and actually am the most familiar with. And they make an attempt to size the equipment, but it's really up to the designer to narrow that right down, to get down to the nitty gritty, to decide what's right based on the capacities for their particular piece of equipment, whatever it happens to be. So when we did heat gain and heat loss calculations, it didn't matter what type of equipment we're using to heat or cool our place, doesn't matter. I don't care. We all got to start with how big's the furnace need to be, or how much heat do we need, and how much cool do we need to do what we need to do, okay? That's what we did last week. So this week, now that we know what those needs are, we need to select equipment that'll meet those needs. So do that. Does it have the capacity to meet those calculated loads? This book here tells us the process to do that. And like I say, the software tries and sometimes guides us in the wrong direction. I'll just say that. So it's really up to the designer to decide to actually implement this. So what do we got? Well, we got, let's see, what do we got? Is that my next slide? Yes. Oh, yeah. Oh, this is a good slide. So for several code cycles, we've lowered the U factors and raised R values in order to, quote, Effective use and conservation of energy, or the useful life of each building. Isn't that what the energy code says? So I'm going to ask you a question, and when you're just going to put your thinking caps on here a minute, okay? So how many windows have you attached a gas line to? When was the last time the insulation in the walls had an electrical connection? Meaning I needed to have gas to run my windows or electric to run my insulation. Clearly never, clearly. So how do we save energy? Do we save energy by raising R values and lowering U values? No, the only reason we save energy is that we actually size the equipment correctly. That is the only way. That's it. Sure, we're going to have a wonderful building thermal envelope. It's awesome. And then we put the same size stinking furnace and air conditioning in there we always have, and what have we done? We haven't saved any energy at all. Not a stinking watt or BTU. Not a thing. So unless we're doing this, you're not saving any energy. You're still probably using more because everything's short cycling and not even working right. Right? Yeah. How much energy does a window use? How much does it? None. None of it at all. So unless you're doing this, you're actually not completing the cycle. That it's the truth, guys. And you just think about it for a minute. Absolutely. This is how you save the energy. And I told you last week, I said, if you are not sure that your builders and your jurisdictions or your inspectors and whoever it might be have that down pat, they got a decent building shell, water resistant barrier, flashing, the whole deal. Thermal envelope, air barriers, all that, they got it down pat. Because do not make them do this design unless that happens, because you can do this design down to the gnat's teeth, right? And it will fail because the thermal envelope isn't good, okay? So now that I've browbeat you horribly about that, let's move on to how this works. Okay, so what we had done here last week, let me see if I can get a little laser pointer business here. All right, so last week we went over kind of the top half of what's happening here. Went over our design requirements here so that those are correct. Went over how we got to these heating and cooling loads, right? So the construction descriptions, things of that nature, our infiltration piece. I don't know if we didn't get into that. Basically, this is just saying that simplified just simply means that we're using an average construction quality, meaning that we're not using actual blower door test results. You could actually get down and use air infiltration rates for each room if that's what you wanted to do. Most guys won't do that. Construction quality, average, not so bad if you start out doing that. That's okay. But you're going to find that once you do your blower doors and things of that nature, you're using semi-tight or tight. But starting out with average is nothing wrong with that. And unless you're building fireplaces that are natural, wood burning fireplaces, you're not going to really show anything there unless you've got those, because those are horribly air leaky. Then we come down into our volume, just the interior above grade volume and AHRI changes per hour and the amount of CFM that's equivalent to that intake. So we're getting down to what we're going to be looking at today, our equipment summaries, our cooling summaries, and the equipment. So I can tell you that the software itself has got this information right here. It's going to have this information. It's built into the software. So depending on what manufacturer they're using, what brought mod, I don't really care. Doesn't matter to me. What we need to understand, though, is that in this particular case, this person used Carrier. Well, if Carrier doesn't have a smaller or bigger furnace to meet the load, so let's say, in this case, it was a 40,000 BTU furnace. Well, let's say they didn't make one. Let's say the Carrier didn't make a 40,000. The smallest thing they had was a 60,000. Well, 60,000 is going to be too big. I mean, oversized technically, but the code allows that if it's the smallest thing that that maker makes, we're good to go. We just move on with life. Same thing with air conditioning. So if it was Trane, I don't care. Doesn't matter. Just because the carrier doesn't make it doesn't mean they have to switch brands. Okay. So we're going to take a look at that. So the AHRI reference number is important because it's a matched. It's actually been tested and it actually says that yes, this particular model of carrier will actually give me a heating output of 40,000 BTUs. So this number, the 92.1, the efficiency of itself, and the input rating is always going to be within the software. Okay, what the software does not know is what to derate for altitude. It has no clue what to do with it. So for you folks that are at 2,000 feet and below, you don't need to worry about it. There is no requirement for adjusting for altitude if you're 2,000 feet or less. That's pretty generic, pretty good. I don't know of any gas-fired manufacturer, manufacturer of gas-fired equipment that is any different than that. It's pretty universal. Okay. So if for those that are higher than 2,000 feet, this is something that they actually have to do. The designer actually has to figure out what that is. Gas-fired appliances will tell you in the manufacturers every single time exactly what the duration for altitude is for every 1,000 feet above sea level. So in Denver, for instance, it's 5,000 feet. So it's either 2% or 4% per 1,000. So it's either 10 or 20% duration. So how would you do that? Well, you take 40,000 times 0.921 because that's just how efficient it is. Then you take that answer times the altitude duration. In this particular case, it was another 10%. So we took that number times 0.9, and that's how you get this 33,000. So it's key that this is done for altitude and gas fired. Now it's going to be different when we talk about air conditioning stuff, and we'll get to it. Temperature rise, this is the key right here for furnaces. Gas fired furnaces, that is the biggie. I don't care how much air you're moving. In this case, we were saying 830. I don't care what you come up with in the math here. As long as when I actually do my test in real life, my temperature rise is within the manufacturer's specifications, and it's usually a range, 15 to 45 degrees, something. That's an example. They're all different, and they're all different between models within the same manufacturer. So there's no, this is what it always is. You have to look it up for each unit. In this particular case, 44 degrees is within that spread. Okay? As long as in real life, regardless of what this math says, okay, as long as I put my temperature probe in there and I'm within the temperature rise, my furnace is working, period. Okay? Because when we get in an altitude, which you guys don't worry so much about there, these, the fan speed charts don't work because it's all tested at sea levels, guys. All tested at sea level. Okay. We'll get into this static pressure business here next week when we talk manual D. So let's move on. We'll get to all of it. All right. Yeah, so here we had that a little bit of an example there, that 31,000. We got carrier because it's just easy. Carriers, piece of cake. Don't know that we're going to actually look at it. Maybe I could. If we've got time, I'll actually pull up the data, and what we're going to be looking at then are just simply screenshots from the software or from these data. So we should be getting this. They should be giving us, and now that particular PDF might be, 70 or 80 pages long. We don't need 70 or 80 pages. We only need the pages that tell us what we need to do. What's the performance? And that's usually 1 or 2 pages. So they can actually divvy that out. So here we're talking about the duration here. So we started with that. We got 40,000 times our 0.921, and then we did another 10%, and that's where we got that. The key is that Manual S does have generic duration factors, but don't use that. No, you're gonna get the footnotes in the performance data. They will actually tell you exactly what it is for duration per altitude. So don't use anything generic. Use exactly what they say. Then you're actually allowed per Manual S to be 40% larger than our calculated load. So we take what our calculated load was, in this particular case, just over 31,000. We take it times 1.4. That means we could have an output capacity of up to, right, 43.5. And of course, ours is less than that. So why 40%? Well, because this is a tough target and we've got lots of different sizes. Also, oversizing on a furnace it's not as a critical energy penalty as it is for air conditioning, okay? So there's plenty of times for those of you that are dealing with altitude know that sometimes the BTUs that you can get in a furnace works, like in this particular case, but the fan, the blower motor, the fan, doesn't have enough power to move the amount of air you need to get the air conditioner to work, okay? So you may have a 40,000 BTU furnace that works just fine, but you can't get a big enough blower to make it work at altitude. So that is one, and probably one of the only reasons that upsizing to the next size furnace, even though it might be much larger than the 40% allowed upsizing or oversizing, it's done for a very good reason, because if it's not done, the air conditioner won't work. Okay, so that's kind of getting into the nitty gritty, but let you know that it's not always as it seems. Real life takes over at times. Oh, so here's a kind of a quick screenshot, and this is the performance data from the actual manufacturer. Okay, so you can see here, this is this certified temperature rise here. This is the temperature rise I was talking about. Okay, so that 15 to 45, and mine was 44. So I would have, as a designer, I would have increased the airspeed. I'd have gone up one more speed to cool that down a little bit, because we want to be kind of right in the middle. This is where we kind of want to be for temperature rise. Let's talk about this certified external static pressure piece. Do not get bent out of shape with this here, okay? What this means is that they don't run the fan at all the different statics, at all the different speeds that the furnace might have, okay? The furnace might have 3 or 4 taps, as they call it. So low speed, medium high, and high. That would be 4 speeds. And they would have CFM at each speed. Well, all they did is they ran it at a 0.1 external static pressure to get the fan speed for that. They ran it at a 0.5 to get the cooling speed, okay? They ran it twice. And then I don't know if I have a screenshot of the fan speed chart, but I'm telling you, the fan speed chart's got way more than 2 fan speeds, right? It's got all the different models starting at a 0.1 external static, and some go to a 0.8 or a 0.9 external static, and they've got CFMs for all 4 speeds. That's just the fan math. So they actually run the test twice and then do math to get all the rest of the speeds, okay? So what I want you to get away from, the takeaway from this is, what you don't want to say is, well, the maximum external static you can have for heating is 0.1, and the maximum you can have for cooling is 0.5. That is just simply not true. It is false. It is simply what they do to test it at, okay? You get plenty of designs that you're going to find at 0.7 and 0.8 external static, and that you will understand why don't you listen to this wonderful program next week? That's when we talk about manual D. So here it is. So at point 1, it was moving 1125 CFM, and at a point 5, it was moving 1215. Okay? That's what it was doing. That's it. Then we get down to the different capacities, and of course, these furnaces you can put 3 different ways as to what it's doing. It's got slightly different efficiencies depending on what it is that you've done. And here is the ticket. So here, right? So gas input ratings are certified up to 2,000 feet. Very, very typical. For anything above 2,000 feet, it says reduce ratings 2% for each 1,000 feet above sea level. So since this particular example was in Denver, I did it 5, right? 5,000 feet. 5 times 2 is 10. Take it times 0.9 and we're good. Never understood why in Canada it's different. No idea what's going on in there. Different test standards, perhaps. Don't know. And this is another thing to be very aware of when you get into the very high CFM. It's bottom returns. Get into high CFMs is the squirrel cage fans love to see the air from the bottom, not the side. This is where you see 9 times out of 10 if they're taking it off the side of the return airplane there on the furnace, or cutting a hole in the side. No, I'd love to see them up on a box while I'm sitting on a box. So that return air has got both sometimes, the bottom and the side. The bottom's the best if you can get it. They really, really like that. So anyway, that's a pretty typical performance data piece. Temperature rise. This particular slide is just showing you what the software is doing behind the scenes. Okay, so it's just a matter of math. Okay, so basically you've got this temperature rise and you have this formula that you put it into, and the software does the math. So the idea is that because we already know this number, and that's why it's important to do the duration, because that's what the actual output's going to be, very close to that, at least math-wise. Okay? That's not changing. So in order to change this number here, what's the one thing, there's only one thing we can change. We change the CFM, the amount of air that's moving through. Yeah. So if we want to cool this down, we'd have to move more air through it, yes? And if we need to heat that up, we need to move less air through it. And all these CFMs come from the manufacturer based on my external static pressure. So at a 0.7, it's actually moving 830 CFM at what we call heat speed, which might be medium or medium high, depending on what my temperature rise is. Yeah, so this is just a formula. If you want to do the math, fine. I just put it in here because that's what software is doing. It at least has a clue as to what that is, because it's just math as long as the designer puts in the right heating output. And just a quick example of what temperature rise is. So basically we've got this return air that's coming down. Look at that, nice, look at that, nice big box on the bottom of that furnace, nice. So you got a temperature probe up here. What's the temperature of the return air? You got a temperature probe here somewhere. That's a big coil. Temperature probe there. Then what's the difference? So what's my temperature rise? Right? How much is it warming from here to here? And if the temperature rises within that range, the furnace is working. If it's not working. It can be too hot and it can be too cold. Okay? Those of you that are thinking that you're bringing in outside air here. Of course, you guys don't get cold there. That's right. I remember you guys saying that, if it gets, down to 40, you guys, we've got, well, what was it? He said it was what, 65, 70 degrees there today? And he's still,
it's a fleece at 65. And if it gets below 40, we cancel school usually.
Well, for you guys, it's all about air conditioning. So you don't want to bring a whole bunch of hot outside air in here. You're never going to be able to cool it down. Okay, we're just looking at the reverse. I don't know how many supply air-only ventilation systems you got. Okay. Airflow, right? And we're going to take a look at that, is actually from the manufacturer's specs. And so at 0.7, we're going to look at what heat speed is here on the charts. And so this is the other one that you would look for, okay? That little performance data piece that I've just cut and paste there. And then this is just a small, this lower portion here is just a small piece of the CFM. So let's take a look at that example. And so this one has 4 speeds, okay? High, medium, low, and low. And so let's just prove this here. So here's a 0.1, and they said it was at 1125 at heating. 0.1, medium, low is 1125. Isn't that amazing? This is what the manufacturer will call it, shipped at heat speed. So it'll be shipped at medium low. Now, the installer can change that. It's just how it's set up from the factory. And here's the other example. So we had a 0.5 and it was said it was 1215. 0.5, 1215. So it'll come preset air conditioning heat or speed at high. Okay. So you can see this is one that goes from 0.1 to 0.8. We'll get to why we did 0.7 next week. Another teaser, okay? One thing here is that if this is all the chart says, and this is as far as it goes, up to 0.8, that doesn't mean I can look at anything that says I've designed to a 0.9. Nope, can't do it. Can't do it. I can interpolate, which means that I can do the math between 0.6 and 0.7 and maybe get 0.65. But what can I do is extrapolate, which means figure out, use the fan math to take this to 0.9 to 0.1 or to 1 inch of static. I cannot do that. This is the chart. That's the one you get to work with, okay? That is a gas-fired furnace very quickly. So, yeah, so here it's like, I don't know, you guys probably don't deal with this a lot. Boilers with indirectly fired water heaters. And so here's a boiler, and this big tank right here is the water heater. And it's just basically a big tank full of water. And what it has inside is another coil that wraps around that it has a zone. So it has its own little zone that then feeds the water heater. And what happens is what they have it's prioritized. And so let's say that, so we're taking a shower here or something, and it's calling for hot water. You know, we need more hot water. It'll shut all the rest of the oven, even if it's heating the house, it'll shut everything down and just heat the water. Yeah, so this was a 135,000 BTU water heater. It just happens to be a boiler, okay? Plumbers will call it a sidearm, but that's just a slang term. Code calls it an indirectly fired water heater, okay? So the thing we run in here is, you know, ski condos. The key here is I might have a condo that might need a, 80,000 BTU boiler, okay? But they've got indirectly fired water heaters. They might have 3 or 4 of these bad boys in ski lodge, but I don't need no lousy 80,000. I need about 350,000 BTUs just to heat that stuff up, because everybody goes skiing, right? And then they all come back and they all want to take showers all at the same time before they head out in town, right? So there's a separate, kind of a different expectation, a different real life there. The key is that you're able to have the controls such that when we're actually heating the house, I'm not running a 350,000 BTU boiler to heat a house that only needs 80, okay? So when we get into those types of situations, it's all about control, okay? It's not, the code doesn't say, I mean, what's the code say? Does the code limit how big the water heater can be? Is there like a limit? No, you can only have a 50 gallon. You can't have a 350 gallons worth of storage for hot water. Ah, I didn't see that. What it says is that we can only size the heating system 40% larger. Well, you can do that, but you may not be able to do. You may have to have a modulating boiler to do it, or more than one. A lot of times there's 3 or 4 of these boilers, and they just all crank up when they're having hot water. Okay, so it's not like you can't do it, but that's how you'd have to do it. Let's see. Oh, yeah. You guys probably do heat pumps there a lot, huh? Air source heat pumps. Is that a deal there? Yes?
Not enough.
Not enough. Oh, man. And in climates like yours, this is not a bad thing at all. But this is what we call a heat pump balance point. And what it's saying is what is my outside design temperature winter heating? Cooling usually isn't the issue. It's usually you have to get a big enough heat pump to heat the place. Certainly here, it's certainly in Minnesota that would be an issue. And it is in Colorado and a lot of places. But down in your place, man, I mean, what's the outside design temperature for you guys? Is it even near 25 degrees?
No.
Probably isn't. So what this is it says, okay, what's my design and what's the output of my heat pump and where do they meet? And so what happens when I need it fast here? Do I need auxiliary heat? We've got a lot of places in Colorado, a lot of places around the country really, that do have air source heat pumps, and it's just an air conditioner. It's just able to heat and cool, can reverse the refrigerant flow, is all it does. But you have backup heat. So for instance, in Colorado, everybody's got a gas-fired furnace, so when the air source heat pump can't keep up, it just flips over to the gas-fired furnace, and it does that automatically. It's all about controls. But yeah, air source heat pumps, that is something to look into for you guys. It would actually be, you still have to put the ductwork, you still have to do all of that. But it might save you some money. As far as energy costs are concerned, there's lots of studies out there that you can look at. But in a lot of places that I help people with, it's just not, air source heat pump, fine, but you're still putting in a boiler or a gas-fired furnace just to keep up. And, oh yeah, well, I guess what this example is that these are just the different ways you can heat, and I don't really care how you heat, you just have to meet your load. Okay, and it all depends on what it is you're using. Okay? In this particular case, electric baseboard, right? The codes say that you can't use it? No, doesn't say that at all. So yeah, electric baseboard's not too difficult, particularly. Well, I need to know what my BTU per foot or the total BTU is for a particular, electric baseboard heater. If I need 1,000 BTUs in that room, well, it needs to have, if it's got 250 BTUs per linear foot, I need a 4-foot baseboard in that room. Not hard. That was easy. Those are easy. Yeah, just don't see that very often. You guys, there's probably, Florida, and there's places, down south where you just don't heat much at all, and they probably do have electric backup for those air source heat pumps, or even ground source type heat pumps. Those are even a little bit more expensive, but they're really efficient to do that. All right. So I'm sure I've done such a fantastic, quick job of running through heating equipment. At least that's the basics. I think that honestly, the biggest thing is that this was just completely over your head. The key is to make sure that you ask just enough questions to know that whoever did do this, the designer, has answers, right? Why does it seem like, your furnace is 250% larger than your load? What's that all about, right? Yeah, just like, tell me why, see, we'll go, right? All right. So that was the easy one. Air conditioning gets a little tougher. It's a little tougher, and it can get a little confusing at times. So I'll try to slow down here a little bit. so that we get it. So the key here, again, is just that screenshot from that very first report that we looked at today. And again, all of this information here, all of this, the efficiency, all of this from here up, the software does a very good job of. It's all within the software. Carrier and the conditioner and the coil that it's in, and the AHRI. The AHRI, which we'll get into in a few slides here, what that's all about. This number here is important because what it means is that this outside conditioner or the outside compressor in the indoor coil have been manufactured to work with each other. It's what they call a matched pair. And there's lots and lots and lots and lots and lots and lots of different matched pairs. Okay? It'll have the efficiency in there in the software. What it won't have is any of this stuff here. These three numbers and how it's split: sensible, latent, and the total cooling. And we'll get into that. Okay? This is another place where the software tries, but really has no clue on how to help do that. Okay? Let's see. Oh, well, here it is. Look at that. So AHRI, Association of Heating and Refrigeration Institute, something like that. I can't remember what it stands for, but this is a screenshot for how they test it. So the standard is good in that it tests all the equipment the same way. Carrier or Train or whoever it is that you've got, all of the combinations and all of the air conditioners are all tested with the same parameters. Okay, that's good. So that the idea that a 2-ton carrier is better than a 2-ton Train. Okay, so they're not doing that. Okay, the bad thing is that it's not always what you're designing to. And so we'll take this test here. Here's a test. It's saying the entering dry bulb temperature. Now remember, we talked about that last week. I didn't bring up the sling psychrometer quite yet. That was the difference between the wet bulb and the dry bulb. Yes, remember? So we have the dry bulb at 80. The wet bulb is 67. It is saying that the outdoor entering temperature on the outside, so the compressor sitting on the outside of the building, the air entering it is 95 degrees. Okay? So you guys are down south. Down south. And what's happening outside for you guys? Is it 95 degrees? What is your outside design temperature down there? Is it over or under 95 degrees?
Usually a little over, but pretty close.
Is it close? Yeah. I can tell you there's a lot of places that it's a whole lot better, a whole lot hotter than that. And I can tell you a lot of places it's a whole lot colder than that. Okay? So what are you guys designing for your diet? Is everybody comfortable at 80 degrees inside their home? Is it good? Is that where you set your thermostat? Remember last week we were actually saying it's 75 degrees. So this is why it's important never just to look at the AHRI data. It's because it's not what the design is. So we're never designing to 80, so instantly this is all wrong for everybody. Okay? It's only good to make sure that we're comparing equipment correctly. Okay? 95 degrees, you might be lucky and designed to 95, but there's a lot of places that aren't that lucky. Okay, so we always have to have the expanded performance data for every unit. that shows us what it actually does at these other temperatures, and the information's out there. It's just that the software only has this information. This is all it's got, and it's wrong. Okay? It's wrong for our needs. It's right for the testing, but wrong for what we need to actually to do. Okay. Okay. Okay, yeah, so just type in questions. If you got questions, type it in and we'll do questions later. That's the way we're going to do it today, okay? Because you can type those in and we'll talk. We'll have time. I'll move on. Okay, so I also teased you last week as to say, okay, remember this report where it got about multiple orientations. So which way is the worst? So if I'm doing a production home, I want to design it to the worst possible way this could ever face, okay? Ever face. And when do we decide we need two different pieces or piece of equipment? Well, this is giving our answer. And so this is all based on our sensible load, which is the heat. That's the hot that we're trying to get rid of. What's the largest here? So it looks like that is definitely the largest. Now, what's the lowest? So if we were to face this, looks like if we were to face the front of this building to the southwest, that load would be just short of 13,000 BTU. Where it's the worst, let's just call it 16,000 for easy reference. So we got 16,000 and 13,000. So the difference between the best way we can face it and the worst way we can face it is 3,000 BTUs. They only make air conditioning equipment in half-ton increments. So that's 6,000 BTU. So the difference between the highest or the worst and the best is 7,000 BTU. We're probably in good shape. We don't need to do another design. We certainly don't need another piece of equipment because there isn't equipment available that does that. But the only thing you're going to be able to get into that maybe is some mini splits, but that's a whole different conversation. Okay. So in this particular case, we just need one design. Okay. Yeah, it's pretty rare unless you've got like a house of glass that's facing somewhere that a typical single family dwelling would need two designs. Yeah, I haven't found very many where we've got more than 6,000 BTU. So for those of you, I keep referring to a ton. So a ton of air conditioning is 12,000 BTUs. How do we get to 12,000 BTU? Well, it takes 12,000 BTU 1 hour to melt a ton of ice. And there you have it. Okay? So 12,000 BTU is a ton of air conditioning. Okay? That's why. This is just a quick screenshot, rotational report from the Elite software, and it gives you the same thing. So this is not the same house, but you would look for the same thing. So this one's 17. It looks like 15 is the next 15 too. So here's one at 262. So again, you know, we're looking at less than 3,000 BTU, maybe a little over, well, no, not even that. A little over 2,000 BTU. So again, in this particular case, we're in good shape. Move on. But this would be for like a production home where I have no clue which way the front door is going to face. But for a custom home, you'll be able to dial right in because you know exactly which exactly which way the front of the house is facing. Let's see. Oh yeah. So what we're trying to do, and especially in you guys areas where you've got a real latent load, meaning humidity in the air, water in the air, they're trying to wring the water out of the air. You will actually have a sensible heat ratio of something that's not 1. Because right now, this one's done for Colorado and it's just dry as toast. And so we don't have, there is no calculated latent load, right? Equipment latent load here, 0. Yeah, generally speaking, there isn't. one, especially if you're bringing in air from the outside, which is this one is. You're not going to see it. And if you do see it, it's very, 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 very small. Generally less than 1,000 BTU. Whereas you guys, it's going to, you know, it'll be pretty heavy. So the idea is that we want to get a piece of equipment as close as we can to the same sensible heat ratio. Okay? Yeah, the plan is to pick the cooling equipment, same or as close as we can, the same sensible heat ratio at the specified CFM, and we'll look at that table here in a second. Okay. All right. All right, so here we're going to start looking at, this is just a very small screenshot of the detailed cooling capacities for the piece of air conditioning equipment we picked out for this particular project. Okay? And so we've got several different pieces that we're looking at here. Okay, so back in the time, you know, whether I said it or not, 75 degrees at 50% relative humidity is psychometrically equal to about a 62, 63 degree wet bulb. Okay, they've now started printing out things here like this, and I'll show you why here in a second. But we're going to be using this one here, the 63 with this little kind of a double T note here to start with. So right or wrong, good or bad, AHRI and AHRI and everybody else decided that comfort is 75 degrees at 50% relative humidity for inside summer design. So that's what we're designing to. All right, so next, I need to go next. Why is it just not moving? Yeah, so we're going to use the 63. We'll look at the footnote here in a second as to why we're using that. And this is something that the designer should be doing for you. You shouldn't have to figure it out. They should just be able to circle it and highlight it and say, this is what I used. So you don't have to like search. You're just verifying that they followed the path. Then you'll notice that there's generally 3 or 4 different CFMs with the different capacities. Okay. Yeah, we'll deal with the altitude here in a minute. So we're going to start with this 800 CFM value. Okay. And so that was in this particular case, we had nothing for latent, and we got about a little over 15,000 BTUs for cooling. Okay. So next. All right. Yeah, so the air entering the condenser, right, the outdoor unit, is the outside dry bulb temperature. Okay. So this starts at 75, and I cut it off. This goes up to 125 degrees. It goes way high. Okay. It keeps doing that. Yeah, so we got Denver is 90, and our design was 90. So you can be within 5 degrees either way. So we could either use the 85 or the 95. We could interpolate between the two if we wish. Right, Soft actually got a way to do that within the software. I don't mind. Let's go to the higher one because the capacity is going to be a little bit less, isn't it? Why is that? Why would the capacity be less the hotter you get outside for an air conditioner?
I can't wait for you to tell me.
Yeah, we're rejecting heat. Is that what we're trying to do? We're rejecting heat. So we're taking the heat from inside the house and through that refrigerant and trying to get rid of it on the outside. And those fans are sucking the outside air through the refrigerant to try to do what? Cool it down. Yeah. So the hotter it is outside, the harder it is to cool that stuff down. The colder it out is, the higher it gets. So you got 21,600. And then if I took down 5 degrees, look, now I'm at 22,720. And if I took it down another 10 degrees, I'm at 23,760. So I've dropped 2,000 BTU just because I'm up 20 degrees. Okay, so it's important. This is important why you're looking at this stuff, to make certain that you're getting the capacity that you need based on what your weather is where you're at. Okay. All right, next. Yeah, so we could take a look at this, and if you guys were doing this, this is exactly the numbers you would use. You wouldn't have to worry so much about excess latent capacity unless you were really dry. Yeah, so we'd have a sensible heat ratio. So what that is you take the sensible capacity and you divide it by the total capacity. If I didn't say that, I apologize, but that's how you get the quote sensible heat ratio. Well, in this case, it's about 0.74. And in our example, we want to get as close to 1 as we possibly can. We're not going to find equipment that gets to 1, but we're going to get closer. Okay. Next. Oh, yeah, here's the little footnote that I was talking about. They used to just give you this one here and you had to do a whole lot of math, but now they've got this where it talks about you're using the 75-degree indoor temperature, which is awesome. Now we don't have to do a lot of extra math because you see everything else was done at 80 and we just learned why, because that's the AHRI standard. Yeah. So Manual S actually gives us a couple of different ways to deal with this excess latent capacity. So let's think about what's happening. Let's just think about what in the world is going on in our furnace here. What are we doing? We're actually taking air, this nice warm moist air, and we're going past a cold coil. That's coil inside the furnace. Yes? Everybody's saying yes. So the more air I'm moving through there, the coil is getting warmer. Do you agree with that? Yes, I'm moving more air. I'm getting that coil warmer, and what's happening less? Well, the colder the coil, the more water will condense on there. Yes, it's physics. The warmer the coil, the less we're getting in condensation because it's warmer. So the more air we move, the more sensible capacity we have. So when we're in these, high, I'll just click through quickly so we got some time here. The idea is that when we deal with very low or a lot of excess latent capacity, we can easily take half of the excess stuff and turn it into sensible. It can happen all day long, not a problem. The other way that Manual S talks about doing this, we can actually derate the air conditioning based on our altitude, and there's some math that we can do for that. But the key is that the manufacturers still haven't told you what to do at high altitude with air conditioners. It's just, it doesn't exist. Nobody's been able to tell me that it exists yet. I've never seen it. Doesn't mean it doesn't exist, I just don't know that it does. And that's why Manual S is handy. But for you lowlanders, you don't have to worry so much. So we got our new equipment, we got up to about a 0.87, which isn't so bad. And we got something that works. We got something that works great. Oh yeah, so altitude, so that the whole idea is, are you moving 1,000 CFM at 5,000 feet if you're moving it at sea level? And the answer is absolutely you are. It's just that you're not, it's the density that counts. So the air doesn't have the same capacity to move heat and cool as it would as if I were at altitude. So we've got to do, we got to adjust, and so we won't spend a lot of time because you guys are a bunch of lowlanders. So this is this whole density correction factor. So in our example, if at sea level in you guys' area, if 800 CFM would work just fine and get the capacity, we got to move 962 CFM to get the same thing. Yeah. Up in the altitude, 5,000 feet, and if you were even higher than that, you'd have to even move even more to get it to work. Hence the need for big blowers. Okay, we'll skip through this. It's just saying it. I got 995. We're in good shape. Move it on high. We're fine. I would be tempted to even go up to the 60,000 because we're that close. This would be a case where we're going up to the 60,000 so I can get a bigger blower here. The 16 just means that I got a bigger blower. I would not mind if the designer did that in this case. Oh yeah, we did that. Yeah, we did that. Cooling equipment, we're good. Oh, I put a little key elements thing together. We're not going to go through that. It just is giving you some pointers and some of the math that I just did so that plans examiners have something to look at, especially at altitude. And that's all I got. So that's me. Again, do not hesitate to send me an email. If you guys are just starting along this path, do not hesitate to call or ask questions or send me a manual J or something that you got, and it'll take me a couple of minutes just to go through it and say yay or nay or help you read it. So what do we got? We got questions or what?
Yeah, I remember one time I was teaching a class to just a bunch of builders, and how I was imploring them to, this was 4 or 5 years ago. I was like, look, I understand if your HVAC guy's your fishing buddy and he's always just put 1 ton per 500 square feet. And that was fine 30 years ago, but I'm telling you, it's not anymore. We're building to the 15 energy code. We're blower dooring, we're duct blastering, we're doing all this stuff. And anyway, 2 or 3 days later, one of the builders emails me back and he goes, man, I believed what you were talking about, load calculations and equipment selection. So I had a conversation with my HVAC guy about it, and he swears he does a manual J, and I'm looking at it, and it's still showing 500 square foot per ton cooling. And I said, well, email it to me. And I'm looking at it, and I'm looking at the plans, and wall, R value, window, square footage, everything's looking good. And then I get to about the 8th or 9th page where it's the ducts, and on the manual J, the HVAC guy put uninsulated sheet metal ducts in an unconditioned attic in Texas. I was like, oh yeah, that'll get that'll get you at 500 square feet to where you want to be. Yeah. So Jim asked, and I'm pretty sure these are updated every 15 minutes or something ridiculous. I know it's regularly. And everyone so a little housekeeping that I forgot in the beginning. If you need ICC CEUs, Liz will send you a course evaluation. Simply answer the course evaluation and she will get you your CEUs. Gil, do you mind sending me a PDF of your slides?
No, it doesn't matter to me. What do you want?
Okay, and I'll attach a copy of the PDF of the slides if you need those for future reference. A copy will go on our YouTube channel of the video, so you can always reference this later. We have a handful of other ones on our YouTube channel as well. But do you know, Jim asks, if climate change is raising the outdoor temperatures, then a higher outdoor temp is needed to properly design the system. How often is the AHRI charts redesigned to account for this?
Well, I just know that you can, I'm updating my software a couple of times a year, okay?
Okay.
And it really is going to be up to the jurisdiction. They can certainly set their own outside design temperatures for winter and summer. Okay. I honestly don't know how often AHRI actually does it. I don't think it's more often than like 5 or 10 years, okay? You can go.
I think it's quarterly, Gil. I think it's more often than that. I'll find out though. I'll find out, and you'll also get a Word document. All the attendees will get a Word document, basically where I've taken the mechanical chapters of the IRC and condensed them into bullet points. And there's a hyperlink to the AHRI outdoor design temperature that might have that information, how often they update it. I can't remember, but I swear it used to be every bunch of years, but I think it's more often than that now, but I don't know. But that's a good question, Jim. Yeah. You mentioned earlier you had to install in matched pairs. Would there ever be a case where you wouldn't install a matched pair?
Not that I'm aware of.
Okay. No, and then Sally wanted you to, I know Manual J allows up to a 30% oversize for variable speed equipment, but she just said her question was, and then she typed it in the chat, sizing variable speed equipment, please elaborate. You got anything else on variable speed equipment?
So variable speed is all fine and dandy, and which is great. That's what I've got. It's the modulating ones or the two-stage ones that they seem to think that Well, this thing might pop up on high stage. It just might. So I'm going to put one in that's way big.
Yeah.
Yeah. You'll always pick the size at the highest capacity. Okay. So I might have, let's say I've got a 100,000 BTU furnace and my load is only 45,000. Well, no. Well, it'll probably, only run at low speed, but just in case it'll run on high. No. Now you're not putting in that. It's just a waste. Because the more than likely is it'll probably never run, ever, on that second stage. Okay. So variable speed is great as far as airflow goes. You almost have to do variable speed if you're doing zoned systems. You also have to think about the two-stage air conditioners, right? Or what they call variable capacity air conditioners, although there are 5 or 6 different stages. But you have to have a variable speed airflow in order to handle that, because you don't need 1200 CFM to run on high if you only have 1 out of the 5 zones running, right? So I've got a two-stage. I got a two-stage AC and just variable speed furnace, but in zone valve, so it just adjusts. If it's just the first floor of the basement running, fan speed adjusts based on what it needs to get the air conditioner to work, because it'll be different based on how much air conditioning you need.
Yeah, how many zones? Well, we are right on time, Gil. It's like you've done this before. We're right on time at an hour. That's all the questions. We'll go ahead and call it a day. I can't thank you enough. Next Thursday, same time, same place, Gil will be giving the conclusion of his JS&D series with the manual D. So looking forward to having you back in a week, Gil. Thanks again. Can't thank you enough. And thanks for joining us, everyone. Fill out the course evaluation and you can get your CEUs. Have a great afternoon, everybody.
All right.
Thank you.